And we're live. So just to jog your memories, this is the time where you're going to stop talking and listen to your teacher. Thank you. This is 1.10. I believe it's called the continuity of trig functions. I'm basically going to rewrite the example that we started yesterday. So no, you don't need to start a new page. Continuity of trig functions and the squeeze theorem. What did I get on the AP test? Are you kidding me? So recall. I don't know why it's always so blurry. I need a new doc cam, I feel like. Yesterday, I had claimed to you that the limit of the quotient of sine of x and x as x approaches 0 is actually 1. And it was kind of a shaky proof. We just kind of looked at the graphing calculator and said, yeah, it looks like 1. But today we're going to use that a little longer, a little more, and then actually prove it. And this is also, the reciprocal is true, namely that the limit as x approaches 0 of the quotient of x and sine of x is also equal to 1. And you don't need to rewrite this because we literally did this yesterday. That the first example we looked at was the limit as x approached 0. I think it was sine of 5x over x. And we said, well, that looks pretty close to what we want, but really we need the argument inside of the trig function to exactly match the denominator. And the way we ended up accomplishing that yesterday was to multiply everything by 1, just a very carefully chosen 1. So then this turned into the limit of 5 as x approaches 0 times the limit of sine of 5x over 5x. Then we've got our matchy. So all I did was put the 5 down here. This 5 stayed out. And this turned into 5 times 1, otherwise known as 5. That was where we quickly got to yesterday. Well, this is about as basic as these examples are going to get. I should have just done this right now, but we'll do it on the next one. What I want to reiterate through the next couple of examples is this thing right here is a tool for you to use. When you get into a situation where you have information that says you need a tool here. Our first attempt on any limit should be the plug and play. Plugging and playing here gives us the sine of 0 over 0, which is 0 over 0. That is information coming back to you that you need some tool. Don't just see a trig function and assume, oh, I need to go to this trig. It could work out fine. Okay? So always plug and play first. And then when you get that information, that indeterminate case of 0 over 0, that's when you go to factoring. That's where you go to conjugates. That's where you go to your theorem. Don't go hunting for problems that aren't there. Make sure that you actually have a problem and then think, what trick can I pull out right now? One of the guys who taught me calculus here, Mr. Spidel, talked about, you guys know Felix the cat, the cartoon character, and he had a bag of tricks. So as calculus students, we're kind of like Felix the cat. We're building this bag of tricks to pull out in certain situations. Don't go diving into the bag before you know what we're looking for. Okay. And sometimes you don't need the bag of tricks. Sometimes you just need to plug and play. So let's see if we can add some spice to these types of problems. And the answer is yes, we can add some spice. Of course, we can add some spice. There's always spice. So for example, if we had, we'll call this example 2. if we have f of x equal to the sine of 3x divided by the sine of 5x, and are tasked with finding the limit of f of x as x approaches 0. Remember, we're Felix Cat. We're not just going to go jumping into the bag of tricks before we try the obvious. Let's try the obvious. Plug and play. When you take your test in a week and a half, I'm not going to say find this limit by factoring or find this limit by using conjugate. I'm just going to say here's a function, here's a limit, find it if it exists. And so on every single one of those problems, your first attempt needs to be plug and play. So plug and play here would be that the limit of our function as x approaches 0 is sine of 3 times 0 over the sine of 5 times 0. Really just the sine of 0 over the sine of 0. What's the sine of 0? 0. Yeesh. So that's the information that's blaring in our face now. It says, hey, we need to use a trick here. We need to channel our inner Felix, grab into that bag of tricks and see what comes out. Well, this is the trick that comes out. Somehow finagling our way to a function where we can apply this a couple times. Okay, so let's do that. Let's finagle, official math word. Let's finagle f of x. So identity can be used. We're looking at f of x. Currently, as constituted, it looks like sine of 3x over the sine of 5x. That doesn't look like that. It's kind of like that, but it's definitely missing a lot. And so the kind of thought process that goes on here is if we're going to build out some quotients that allow us to use either this side or this side of our identity, and taking into consideration what we already have, we need to identify what's missing that would make this look like these. And so I think the best way is to do it numerator and then denominator. So ask yourself, for the sine of 3x, what are we missing from the bottom to allow us to be able to do sine of x over x? Not just 3, but 3x. I'm going to use blue for that. We want a 3x on the bottom. Are we allowed to do that? Can we just multiply by 1 over 3x? But what can we multiply by? Yeah, 1, which is disguised as 3x over 3x. Okay. So now, and I'm going to kind of do like some messiness here. We can see that this is flowing in the right direction. Our kind of blue amoeba has the makings of the quotient we're looking for. Well, then what about the sine of 5x? We now have sine in the denominator. We need to match the argument in the numerator, meaning we are missing a 5x. But same story, we can't just willy-nilly multiply a function by 5x because we feel like it. We need to multiply that function by 1. So we'll do 5x over 5x. So then the amoeba comes back out, and we can kind of see the makings of our second quotient that will allow us to use the identity. So this is kind of the creative step here. This is the part that you're required to look and see and make a decision. What do I need here? What am I missing? How can I get it? Now we're just going to rearrange. So we're going to hit this with the limit. The limit of f of x as x approaches 0. But now, using this definition of f of x, and I'm going to rearrange it in a nicer looking way. I'm going to do the sine of 3x. I'm going to do this in blue, I guess, just to have color code. Sine of 3x over 3x. And I think, especially when you got like a lot of stuff going on, I like to kind of lightly cross out what I'm writing down. So, okay, I took the sine of 3x, I took this 3x, and I'm not going to try to rewrite that. Then the second quotient that we want is the 5x over the sine of 5x. Same thing, let's cross out one of those 5x's and the sine of 5x. And if you're careful, somehow accounting for what you've written down so far, then you won't forget, hopefully, what's left. The leftovers are the 3x on top and the 5x on the bottom. I think I got everything from here, and I just rearranged it here so that it looks the way that will be helpful to us. There's one of my quotients. There's the other. This one, what's x over x? Let's cancel those out, because otherwise we're going to run into trouble. We'll have 0 over 0 still. That's a nice byproduct. The x's go away. And then breaking this into its component parts as a product of 3 different limits. We'll have that the limit, this limit here is the same as the limit as x approaches 0 of 3/5. I'm just writing this one out front, times the limit of the sine of 3x divided by 3x times the limit as x approaches 0 of 5 over x divided by the sine of 5x. This makes us happy because those ones are now 1. This guy, what's the limit of 3/5 as we approach anywhere? 3/5. Both of these limits are 1. And oh, happy day, the limit of that function as x approaches 0 is 3/5. So if I were to classify these first 2 examples, this one's like super easy. This one's like, I call it medium. Like this is 100% absolutely positively fair game for something on your test. Okay. And the one we're about to do is going to be harder, but still, you know, fair game. Back to kind of the tongue lashing that I gave you guys yesterday. Remember, this is the work of the one guy in the room who has a degree in mathematics. And I feel that basically all these steps are necessary to show. So if you're showing less than this in your homework, I'll probably still be a softie and sign it and get you 4 points. But remember that day of reckoning on the test, you need to convince me you know what you're doing. And this is the self-convincing that Mr. Smith, the guy with the math degree, has to do when he does it. you're doing less than that, just saying, show your work. Don't be afraid to kill some trees. Our environment is screwed anyway. Might as well learn us some calculus while the world burns, okay? You ain't gonna learn calculus if you don't show your work. I guess I probably shouldn't say that on the recorded version of this. It will be live on the internet for anyone. I love the environment. Okay. Trees. Yeah, did we figure out who disliked? Was it your class? Or it was first period, right? Yeah. All right. No, the case is still open and active. Okay, so let's do that harder example. I think it's not even in my notes, it might be in the book. And this is where we find out who paid attention the past 2 years in Honors Algebra 2 and Honors Pre-Calc when we learned about Trig. So if first period is any indication, it might be a bit of a yard sale. Because like very simple trig stuff, I was getting crickets. I am not, and I think you'll hopefully pick up on this if you haven't already, I am not like stickler about like super random formulas and stuff like that. I'm way more into like intuition, but there is some like pretty basic trig stuff that you need as a basis in order to then use the intuition to get to the formulas that I'm not going to make you memorize, if that makes sense. And so I will be a bit of a stickler about like, what's the definition of tangent, okay? Or what's the range of your sine and cosine stuff? That's stuff that we need to be able to conceptualize and understand that it comes from the unit circle and all that. And so that'll come out over the next hour or so. But I'm probably never going to ask you to memorize the double angle formula. Because if you put a gun to my head right now and ask me to tell you it, there'd be blood spatter all over that wall. Because I got limited RAM up here. And I don't memorize stuff that I can look up in a book in general. Okay? But there is a part of trig that you need to just have. Okay? And so we'll see some of that today. So let's quit dance around the issue and let's just look at what this looks like. We need a second. Yeah, I'm gonna go to the other page. Might be long. This will be example 5. No, I don't know what happened to example 3 and 4. Example 5. We've got some function called h that looks like twice the tangent squared of x divided by x squared.
Tangent squared.
Tangent squared x, yes. Which right away, there's some, trig notation that could screw us up. Tangent squared x is the tangent of x squared. Okay, sometimes I think we're like, oh, it's some different function. No, it's tangent of x times the tangent of x. We use this notation because if we put it after, that would be hard to distinguish from when we're talking about the tangent of x squared. Okay. But, getting ahead of ourselves, what is the limit then of h of x as x approaches 0? Well, as always, we'll plug and play. We don't feel good about the bottom, but maybe the top will surprise us. So the limit as x approaches 0 of h of x, we plug and play, tells us twice the tangent squared of 0 over 0 squared. So we know the bottom's going to blow up, but if by some chance the top turns into a constant, then we're stoked, because then it's just a vertical asymptote. But what's the tangent of 0? What is the tangent? It's the ratio of
Sine over cosine. What's the sine of 0? What's the sine of, sorry, what's the cosine of 0? No, 1. So what's 0 over 1? So what's the tangent of 0? 0. So yeah, this is the big middle finger, the indeterminate. We don't know what's happening. Okay. If this had been the cosine squared of 0 up top, and this had turned into 2 over 0, then we would say, oh, it increases without bounding. I'd be like, oh, okay, cool. 0 over 0, no such luck.
How do we know it increases?
I just guessed. I guess it could decrease. Well, that's a deep subject. Let me think. Right? No, because cosine. Whatever. That's not what we're talking about. What we are talking about is this one that has tangent. So now we're looking at it, and we put on our little furry ears, and we're Felix the cat, and we're looking at 2 times tangent squared of x over x squared, and we keep flipping back, and we're like, I don't see where we're going to be able to pull this one out of the bag, Felix, because I got tangent, and you're telling me I need sine. What did we not 37 seconds ago say that the tangent was, Gunderson?
Sine over cosine.
Sine over cosine. So let's throw that out and just see what happens. A lot of times when we're messing with trig stuff, you just kind of throw stuff out and see what happens. And so the thing that we're going to throw out is our knowledge of the definition of the tangent ratio as the ratio of the sine to the cosine. Meaning, h of x 2 times tan squared x over x squared. We can instead write as 2 times, yeah, 2 brackets, sine of x over the cosine of x squared, all divided by x squared. Because again, tangent squared x means tangent of x squared, and then the tangent of x is the sine over the cosine. Well, now at least we've got sine like at the party. That's a good start. But this is like pretty far from that guy. Let's keep finagling. Finagle until you get where you need to go. Let's call this 2 times sine squared x over cosine squared x divided by x squared. And this should be making you like physically uncomfortable that we've got double vinculi. Double what? We know what the fraction bar is called? It's not called a fraction bar, it's called a vinculum. Everybody say vinculum. Vinculum, the real word, V-I-N-C-U-L-U-M, vinculum. And we don't like 2 vinculums in one expression because, I don't know, just we don't like it. So here's what we're going to do. We're going to do the old trick. When you got 2 fractions, when you got a fraction on top of a fraction, double vinculum, go. And we're just going to squeeze that down. Okay. And so this can be written as, let's kind of cruise back over to the left. I don't know why I ended up over there. This turns into twice the sine squared x divided by x squared times the cosine squared x. Anybody see it? Anybody see it? What do we see? How many sine of x's are really here? Sine of x times the sine of x is the same as sine squared x. X squared really means what? X times X. Oh. And we'll leave cosine squared X alone. Oh, minus. No. Just look what we have. Now we have a sine of X over X and a sine of X over X. What were we looking for? We were looking for sine of X's over X's. Ooh, yeah. Let's see what happens now. We finagle our way to something that looks like it might be friendly. So we're going to revisit this limit of h of x as x approaches 0. But now we're going to use this definition of h of x and all this lovely sleuthing, finagling, rearranging. And this will be the limit of 2 times the sine of x over x, take care of that first one, times the sine of x over x, there's the second blue amoeba, times, well, I've still got the cosine squared x down in the bottom. So let's just call this 1 over cosine squared x. And I heard somebody say, well, let's turn that into 1 minus sine squared x, but then let's hold off on that. Let's just see what happens if we plug and play here. Well, if we plug and play, this turns into the product of 4 limits. The limit as x approaches 0 of 2 times the limit as x approaches 0 of the sine of x over x times the limit as x approaches 0 of the sine of x over x. Remember, we got 2 of those, times the limit as x approaches 0 of 1 over the cosine squared x. Feel real good about these first 3 limits, limit of a constant, and then our 2 identities. Let's kind of peek ahead to the end here. Is it an issue to have the cosine of 0 in the denominator? Okay, no. Because cosine of 0 is 1. So cosine in the denominator as we approach 0 is fine and dandy. It's when sine is approaching 0 that we freak out. So here, the limit of a constant, is that constant? 2. I've got my formula or my theorem twice, times 1. E displace, plugging into 1 over the cosine squared. We just said this is 1. So this is 2 times 1 times 1 times 1 over 1. That's a lot of 1s. This limit is just 2. That was some fancy math there. But not that fancy, you know, just requires you to know that the tangent function was the ratio of your sine and cosine. What do we think? What do we think? We do that? Yeah, so we got one more example, and then we'll take a quick break, and then we'll prove this guy. So I'm not going to try to do any smooth convincing here. I'm just going to put in all caps other trig trick for our bag. The other trig trick for our bag. We've got the one involving sine. It'd be nice to have one that lets us out of sticky cosine situations. And what that one is, looks like so. That the limit as x approaches 0 of 1 minus the cosine of x over x is equal to 0, which in turn is equal to the limit as x approaches 0 of cosine of x minus 1 over x. Let's just quickly convince ourselves that this is an issue, that this ratio is an issue. Note that if we plug and play the limit of x over 0, 1 minus the cosine of x divided by x, we would get 1 minus the cosine of 0 over 0. We just said that the cosine of 0 was 1. We get 1 minus 1 over 0, 0 over 0. Eesh. So that's why we need this theorem. In this case, it turns out to be 0. Also note that just as in the case with our sign identity, with first identity, argument and denominator must match. The whatever is in the cosine has to match what's down here. So we'll do a real quick example of this and then take a quick break. Does the timing of that break work out for you, Regan?
Yeah.
Okay, good. I'll make sure you're mentally engaged. Yep. Okay. Example. Oh, new page. How about that? What are we gonna call this? Example 3? Sure. Example 3. Oh, that could be a fun one. No, you know. So f of x is equal to 1 minus the cosine of twice x over 4x. And I believe they're going to want us to find, nope, find the limit of f of x as x approaches 0. I need to put in for a new doc camp. This one sucks. How not clear it is. So let's plug and play. See what happens. Limit as x approaches 0 of f of x would then be 1 minus the cosine of 2 times 0, all divided by 4 times 0. I don't have a warm and fuzzy about the bottom. That's definitely going to be a 0. On top, though, let's see. 1 minus the cosine of 0. The cosine of 0 again. Damn it. So this is the indeterminate case. But, you know, that thing we're starting out with looks pretty similar to what we need. That identity we just saw. The other trig trick says if we have 1 minus the cosine of something over that something, that limit is 0. Well, we don't quite have the something, but it's pretty stinking close. And this isn't actually going to require us to add anything. Everything we need is already there. let's finagle. The limit of f of x as x approaches 0 is the limit of this guy, which is 1 minus the cosine of 2x over 4x. But I don't really need a 4x on the bottom. I just need 2x's. This is not a case of trying to add something, but rather trying to take something out. And the way we can accomplish that is by factoring. We recognize that 4x's is double 2x's. Everybody okay with the fact that 2 times 2x is the same as 4x? Oh, well, now there's something there. Now we do see this 2x in the denominator. Well, what do we do with this guy? Well, anytime we've got a whole number in a denominator, we can turn that into a multiplication by its fractional equivalent. What you talking about, Smith? I'm talking about that this is really the limit as x approaches 0 of 1/2 times 1 minus the cosine of 2x over 2x. Don't believe me? Just multiply this out and get back here. Just factor it out of 1/2. Okay, so now we can turn this into the product of two limits. Limit of 1/2 times the limit of this whole mess. But luckily, we have an identity for this whole mess. The limit of the constant is still just 1/2, but the limit of this quotient, we're being told, is 0. So the entire limit is 0. I got 10:54 on the dot. We will resume at precisely 10:59. Take care of whatever you need to take care of. Maybe throw those lights on for us so we can see you asleep. Got one? Oh, no. He's awake. Close one.
So is the answer always going to be 0?
No, because it's not always going to be a product. Thank you.
You're welcome.
What a day. Tuesday.
What year did you graduate high school? My older brothers. They graduated, my oldest brother graduated in 2007. And Jack was that, and then Kevin was my other. You know him? He went to.
You're Jack looking little sister?
Yeah. Jack and Kevin was that, and Kevin went to.
Man, I don't know.
What? Yeah, they're my house. Yeah.
And Jack went to UCSD, so I have a bunch of friends at UCSD. They haven't seen him for 15 years, but.
Oh, that's so cool.
Yeah, Jack,
Yeah, he's actually living in Australia with his wife, and he lives in Melbourne, and he was trying to be a nurse, but since he like moved there, I think he's still kind of like figured out, especially with COVID, it's like hard to get the jobs and stuff.
Yeah.
But yeah.
Next time you talk to him, tell him that Nick Smith is your graduate senior.
Okay.
Too funny. Do you have any kids?
No,
No.
not yet, at least.
Yeah.
That's a cute dog though.
Cute dog. Or anybody. So I taught your brother for, I taught Christian for 2 years and that never came out.
Yeah, I don't know. I was
All right, I got 10:59. One of you front girls, you hit the lights. So before we get started into the next half of our lesson, on Sunday, the missus and I took Nora to the Dodger game. So our first trip to Dodger Stadium with the Nugget. And the Dodgers won, but the stinking Giants just won't stop winning. So still 2.5 games back. But it was a good day. All right, now that I softened you up a little bit, let's prove this bad boy. I personally enjoy this proof. I think you'll find that I'm not, in terms of like middle, far right is prove everything, far left is prove nothing. I'm kind of towards the left. I'm gonna prove some stuff to you in this class, but not everything. Sometimes I think it's good to see. I think for most of us, unless we are going to be pursuing a degree in mathematics, proofs aren't that important. You're just gonna go and use calculus to get a science degree. Whatever. So I kind of find the balance there. But if there's a cool proof or one that is of outsized importance, we'll do it. I think this is a pretty cool proof. And within the proof lies the last topic of our chapter, which is the squeeze theorem. So this is kind of double whammy of a proof, is that it allows us to, with confidence, continue to use that which we have already been using, namely this trig limit identity. And it also introduces us to what the heck does the squeeze theorem mean, what to do. So with that little lead in, let's do, I'm gonna do a fresh page. You might be able to squeeze it into this last half of the page, but I don't feel good about that, so I'm doing a fresh one. So recall that we were like pretty sure that the limit of the sine of t over t as t approaches 0 is 1. I'm pretty sure. We looked at the calculator, it seemed like it was 1. But like pretty sure is not necessarily a high enough burden of proof for most things in math. We like to be very sure, beyond a reasonable doubt. And so we're going to prove it. And I like this proof because it starts out from a visual proof, starts out from a geometric proof. So what we need to do, and as neatly as you can draw this, the better your life will be, is we're going to draw a unit circle. It doesn't need to be huge, but it needs to be big enough to have some detail in it. We're going to be drawing some stuff within the unit circle. There are 2 lines for it. I'm just gonna kind of freewheel this. Oh, that was so bad. Yeah, really, the only quadrant that matters is the first quadrant, though. The first quadrant looks okay. That is a terrible circle, though. Oh, I had a compass too, you dingleberry. Oh, bummer. Anyway, first of all, we're going to restrict t, which is our angle, to be in the first quadrant. So between pi over 2 and 0. Yeah, let's remember the unit circle starts at 0, goes to pi over 2, pi, 3 pi over 2. And so this proof just starts with an angle that we, for the purposes of our proof, are going to say is between 0 and 90 degrees, between 0 and 2 pi radians. And so let's just draw some angle in that first quadrant and label it t. I'm going to extend the side of the angle, the terminal side out quite a ways. And this is angle t. There's some points of interest that have already emerged here. We're going to call the origin A. We're going to call this point here D. We're going to call the intersection of that terminal side of your angle and the unit circle B. Somebody remind me what the distinguishing characteristic of the unit circle is? The radius is 1. That's why we call it the unit circle. So if the radius of this guy is 1, anybody want to wager a guess what the coordinates of point D must be? 1, 0. That was the easy one. This is the one that the crickets in first period concerned me greatly about. What are the coordinates of B? Not X and Y. There is an X coordinate, there is a Y coordinate, but we can be more specific than that. Gunderson.
So 1 minus x.
What is the unit circle usually used in relation with? Cosine of x and the sine of x. The unit circle, every point around the circle is given by the cosine of x for the abscissa, the x coordinate, and the sine of x or sine of t for the y coordinate. So B is, I'm gonna write it to the left, is cosine of t, sine of t. Okay, all right. Maybe I'm getting a little ahead of myself. That's okay. We're going to draw a fourth point. And the fourth point is going to live directly on top of D, but live on the ray that serves as the terminal side to our angle. And so we're going to call this one E. So we got kind of a lot going on here. We've got this angle T with its terminal side. We've labeled some points here. We're not really sure where we're headed with this. And somehow we're going to prove that the sine of t divided by t is 1 as you approach 0. If you say so, Smithy. So here's how we're going to start. We're going to start with 3 physical shapes, 2 triangles and a sector. So the first shape, I'm going to use green, is the triangle ABD. I'm drawing the third side here. We've got triangle ABD. Then maybe let's use, I don't know, purple. Purple. There's my purple. There is also a sector of our circle called ABD that goes, we're going purple. Would everybody be comfortable if I made the following claim? That the area of triangle ABD, I guess I should use purple here, that's what we use colors. The area of triangle ABD is less than, oh, you big dingus, that's supposed to be green. Oh well. Try to be clever and I mess it up. But do you agree that the green triangle has an area that is always smaller than the purple sector? Yeah. No matter where you put T, that sector is going to have a little more area. So this will be the area. I don't really know what the sector symbol is, so I'm going to say area of sector ABD. Well, deep subject. If we were to use a blue marker and outline the bigger triangle AED, would you be pretty comfortable continuing this inequality to include the fact that the sector area will be smaller than the area of triangle AED? Sorry. It just kind of, this proof starts with basically a visual affirmation. The green triangle, ABD, has an area less than the purple sector, ABD, which in turn has an area less than the blue triangle, AED. Anybody have a philosophical issue with those statements? Okay, because everything flows from here. Well, We know how to find areas of triangles and sectors, I think. Definitely triangles. Let's start there. What's the area of a triangle? 1/2 base times height. Gold star. Remember geometry. To the left side. And we're gonna skip the middle because I think some of us forget that. But the right side is also 1/2 base times height. Ooh. What about the area of the sector? Go. Thomas.
Isn't it the radius times the angle?
Radius times angle and radians. Not sure I like the attempt. So herein lies something I mentioned earlier. Yeah, there's a sector area formula. Yeah, you might have memorized it at some point, but I don't see a bunch of hands in the air right now telling me what it is. Here is like what would make me happy as a math teacher is if you got to this part of a problem and you're like, I'm pretty sure I've seen this before. I'm pretty sure there is something here. Let's just break this down. What's the area of the full circle? Pi r squared, but let's be more specific for this circle. It's just pi, okay? Because this is a unit circle. The sector area of any circle is going to be the fractional component of a full rotation of that full area. Okay, so if you had a 180-degree rotation, you'd have half of the area of the circle. So we just need to find the appropriate fraction that t is of a full rotation. What's a full rotation? Be calculus student, please. 2 pi. So, and I'm going to write the whole thing here, and then we'll fill in what we can. We know that the area of any circle is pi r squared. But we don't want the full circle. We just want the fraction represented by a rotation of t radians. Well, the fraction is t radians over the full rotation of 2 pi. Okay. Well, let's take care of this middle part because this will actually all kind of turn nicely. Because I mentioned this is a unit circle, so r squared is just 1. The pi's cancel out. And so this middle business is just 1/2 t. R is 1. Pi's cancel, we get 1/2 t. That's kind of nice. So now the area of the sector is solely dependent upon our choice of t. The outsides are going to require a little bit of work. We need to figure out what the bases are and what the heights are. The bases turn out to be pretty straightforward, but the heights, we're going to have to do some work. So I'm going to drop a height in the green triangle. And I'm going to call it h sub 1. And then we already have the height as a side in our blue triangle. I'm going to call that h sub 2. I'm going to stop using colors because it's getting obnoxious. The left side then will be 1/2. And I guess we should call those base 1 and base 2, but oh wait, they have the same base. We'll call this base 1 times height 1. The right side is 1/2, still base 1. These two triangles share a base, but now the height is height sub 2. Yeah. What is the length of the base here? 1, both times. Unit circle comes to the rescue again. And then we already sort of cheated here. I should have waited to make this revelation. But the height of our first triangle, our green smaller triangle, corresponds exactly with the y coordinate of point B. And what did I shame you guys into remembering the y coordinate of point B needs to be? Sine of t. So this left side of our inequality suddenly becomes one half of the sine of t. 1/2 times sine of t, because h sub 1 is the sine of t. What about h sub 2? Let's throw back to some like geometry right triangle trig here and see what we can come up with. If we were just looking at the blue triangle as a right triangle, would you be okay if I claimed that the tangent of angle T is the opposite side from T, which we're going to call h sub 2? Or actually, no, we're going to go even further back. We're going to call it ED over the adjacent side, which we'll call AD. Are we okay that ED is the opposite side? AD is the adjacent side, opposite of our adjacent, TOA, SOHCAHTOA, yeah. Well, let's fill in what we know about ED and AD. ED is this height of our triangle, which we wish to know. AD is what? 1. What? You're telling me that the height of that second triangle is actually the tangent of T. Tricky, tricky. The book proof kind of just like blows past this. Like it uses this fact, but doesn't do much explaining. All of a sudden the tangent of T just shows up. So hopefully that helps see, oh yeah, that's why that is true. So then we fill that in. We have 1/2 the sine of T is less than 1/2 T, which in turn is less than 1/2 B sub 1 is still 1. And then we just figured out that h sub 2 is in fact the tangent of T. So this is pretty awesome because now we have confirmed what our intuition was telling us, that this relationship between the small triangle, the sector, and the big triangle is independent of what the size of our angle is. No matter what we choose for T, this will be true. T can be super, super small, or it can be 89 degrees. It'll still hold true. But now we're thinking, okay, how does this get us to this? Well, I'm going to give you kind of the sneak peek to the end. And why we call this the squeeze theorem is that we're going to attempt to squeeze in between two known quantities our unknown quantity. In other words, we want this middle guy to end up looking like this guy, and then hope that whatever is to the left and right, we can figure out. And if we get lucky and what's to the left and the right are the same, if something is less than one thing and greater than that same thing, it's probably got to equal that thing. So that's our end game here. And it seems like we're kind of a long ways off from that, but not as long as you think. Our first move to move us in that direction is to get rid of the 1/2s. We don't need them. You don't need them. I don't need them. There's 1/2s in all three parts of our inequality. So let's just latro. This is really the sine of T is less than the angle T, which is less than the tangent of T. And that's true for any first quadrant angle. Mr. Smith, why don't we just start with that? Because you probably wouldn't have believed that if I just said it. But now we have some pretty good logic behind it. So I don't know, man. Sine of t over t. So let's remember that there's like an equivalent t over sine of t that will work as well. What if we like multiplied everything by 1 over sine of t? Would that start to make the middle look a little bit more like what we wanted? Would you have ever thought to do that on your own? Probably not. That's why we're going through this together. So let's do it. We're going to multiply everything by 1 over the sine of t. Now, I hope that somebody out there is like, wait, and feeling at least a little uncomfortable about this. We're multiplying an inequality by an unknown quantity. Why should that fill you with some amount of existential dread? Thomas?
Because it's negative.
If it's negative, then yeesh. So anytime you try to do a multiplication with an inequality by some unknown thing, you need to be very careful. Because if that unknown thing turns out to be negative, you have fundamentally changed the nature of that inequality. So when we do this, we need to kind of carefully assure ourselves that we're not wading into those murky waters. So do we have any indication about the positive or negative nature of 1 over the sine of t, Mr. Lenthal?
We know t is in the first quadrant.
And how does that help us?
Any sine of any angle in the first quadrant is positive.
Whew. Everybody follow that? Because we restricted t to be a 0 to 2 pi over 2 angle, the sine of any such angle, and indeed the sine of any angle in the first 2 quadrants, must be a positive number. Okay. Sine itself is not always positive. As soon as you drop down into the the third or fourth quadrant, sine can definitely be negative. But as defined in this proof, it cannot be. So we have this assurance that this thing is greater than 0 since or because our restriction of t between 0 and pi over 2. Okay. Dodge that bullet. So let's multiply. Every last part of this is divided by sine of t. What's sine of t divided by sine of t? 1. The middle now looks like t over sine of t. And this last part, I'm going to do a quick sub here and call the tangent of t the sine of t over the cosine of t. And we're multiplying by 1 over the sine of t. Oh, sine of t's go away. And now we've got that 1 is less than t over the sine of t, which is less than 1 over the cosine of t. But I really kind of want to finish with the reciprocal of this. It'd be fine to prove it this way, but not quite as satisfying. Anybody want to impress me with your inequality knowledge and tell me what we do if we want to reciprocate an inequality? I know, Mr. Smith, you're asking hard questions. Do we agree that 5 is less than 7? If we reciprocated that, 1/5 and 1/7, is it still a less than there? Heck no, 1/5 is greater than 1/7. So it's totally fine to to reciprocate whatever's in an inequality, but if you do so, you got to flop the sign. And so I want to do that. I want to turn this into sine over t and then flip everything. We'd have cosine of t on the left, and 1 over 1 is still 1 over 1. Okay, so I flipped everything and then flopped it, and then put it in the right order. And now that middle part looks exactly like it did in our theorem. And now let's check out this magic. We're gonna finally do the limit here. And while we haven't explicitly stated this, if you have an inequality and you hit it with the limit, the truth of the inequality is maintained. Okay. So, and this should be a t, I'm sorry. So in other words, if the cosine of t is less than the sine of t over t, which is less than 1, then it also must be true that the limit of the cosine of t as t approaches 0 is still less than the limit of the sine of t divided by t as t approaches 0, which is still less than the limit of 1 as t approaches 0. Feel the squeeze start to tighten. Not yet, maybe. Let's evaluate these. We still won't be able to evaluate this. I don't know what that is. That's why we're doing this. The left side, though, what's the cosine of 0? 1. Ho, 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 is less than the limit of the sine of t over t as t approaches 0. Riddle me this. What is the limit of 1 as we approach? Now finally, riddle me this. If something is greater than 1 and also less than 1, what do you think that thing probably is? 1. That thing is 1. And so we have squeezed this unknown, unwieldy thing in between two things that happen to be the same. And when we do that, we can guarantee ourselves with a very high level of certainty, way better than pretty sure, that this thing must share the value of the two things that's being squeezed in between. And so we get to conclude that the limit of the sine of t divided by t as x approaches 0 is in fact 1. Might do like a little QED or a little, oh, can't see that, can't you? Damn it. Still on my phone. So now we know that. Before we were kind of just like pretty sure. It matters a whole heck of a lot. So we're gonna put t here. Thank you for catching that. So it matters insofar as everything matches. If you wrote this as the limit of sine of x over x, then you'd have as x approaches 0. Whatever variable you write here, that must be what the variable in the limit is. T, I think, was an easier choice to use here, just so we weren't getting confused with x and y coordinates. Okay, so let's put a bow on this proof and on this idea of the squeeze theorem, and then we'll do 2 examples with the squeeze theorem, and then call it a day. So basically what just happened is that in deriving the identity, and sorry, just to be clear, this proof works just as well if we hadn't done the reciprocation. If we had just gone from here, this still goes to 1, this still goes to 1, and so this guy also squeezes to 0. That guy still squeezes to 0. So we're not going to show that separately, but just verbally saying, yeah, that also works. Sorry, 1 squeezes to 1. Squeezes to 1 as we approach 0. Okay, So what we did in deriving the identity, we squeezed our desired difficult limit between two nicer limits. But not just any two limits. It's not just like, oh yeah, this one's bigger, this one's smaller. It works because those two nicer limits shared a value. So between two nicer limits that shared the same value. And because we began with a statement, in our case, relating all the way back to like triangles and sectors, but we began with a statement that promised that our limit, our difficult one, fell between the other two. It also must share those values. Share their value. So it's a pretty ingenious way to prove something. Like, hey, I don't really know what to do with this, but I can like force it in between these two things that I know have the same value. And we'll do an example in a minute where one of the like most common ways to use the squeeze theorem is with polynomials that have been flipped on top of each other. It's like a parabola, and then you flip it on top of each other. At that vertex, their limit is the same. And if you know your function squeezes in between those two vertices, then they share the value. So we'll see that in a second. So this is just a way, another tool that can be used when we're looking at a specific function that is just not that fun to work with. Throw it in between two that are. So let's do an example that involves a trig function, and then we'll circle back to a second example that is a little more just forced squeeze theorem. So let's do example, I don't even know example one. Call it example 5. Let's find the limit as x approaches 0 of x cubed times the sine of 1 over x. Sure, we'll call example 6. I have no idea what example number we're on. I just put numbers out there. Come on. What do you expect? Well, new subject. What's our first play with any limit? Plug and play. Let's plug and play. Limit as x approaches 0 of x cubed times the sine of 1 over x. Well, plug in a 0 for x, cube it. So far, so fun. The limit's allowed to be 0. We're okay with that. But then the sine of 1 over 0, ooh, it hurts. I don't know what to do with that. You know what to do with that? So we reach into our bag of tricks. And most likely on a squeeze problem theorem question on a test, I will say use a squeeze theorem. So you're not just groping mindlessly into your bag of tricks. I'm going to tell you specifically which trick to pull out. And in this case, we're going to look at the squeeze theorem. Now, especially a squeeze theorem problem that involves a trig function. And especially if that trig function is the sine or the cosine. You can take this to the bank, Zaharic, that you are going to start your problem with the following inequality. That the sine of theta, the sine of any angle, we have a built-in inequality for both the sine of any angle and the cosine of any angle. Because we have a built-in restriction on its range. What's the biggest that sine of theta is ever going to be? +1. What's the littlest that sine of theta is ever going to be? -1. So, like, open your eyeballs if you're falling asleep. Look at that. When I ask you a squeeze theorem problem on the test, this is probably where you need to start. This line right here. Do you even know what it means? Probably not, but you should, because unit circle, the x coordinate can't be bigger than 1, can't be smaller than -1, no matter how many times you spin. Just always going to keep hitting all the values between 1 and -1, 1 and -1, 1 and -1, 1 and -1. Unit circle, unit circle, unit circle, unit circle. Trig's not hard. You just got to think about it. Okay. So now we've got an inequality. Is there a way to finagle this situation inside of this situation and hope that the outsides are the same? I don't know, but we're sure as heck going to try to find out. So if the sine of theta follows that inequality, is it safe to say that the sine of 1 over x also will hold true inside this inequality? Is 1 over x an angle? Does any angle we put into sine fall between -1 and 1? Yeah, so this is fair. Okay. So now we do what we kind of did at the end of our proof, which is look at what we've got in the middle, look at what we want in the middle, and say, how do we get what we want to look like? How do we get what we have to look like what we want? What are we currently missing from the middle in order to try to squeeze our theorem or squeeze our limit? X cubed. Okay, okay. Remember this moment came in our proof where we're multiplying by 1 over sine of t, and we're able to kind of convince ourselves that 1 over sine of t was always going to be positive, and so that we didn't need to worry about breaking into 2 different cases depending on if 1 over sine of t was positive or negative. Remember how nice that was? It felt good. Well, forget that, because do we have that same assurance for x cubed? X cubed can certainly be negative. If x is negative, x cubed is negative. And so this is not going to be your favorite thing in the world, but we're going to have to break this into 2 cases. That because x cubed can be less than 0, we need cases. Do we have to? Yep. So, case 1, we'll do the easy way first. If x is greater than 0. If x is greater than 0, then what is x cubed? Positive. So we can do our multiplication without worrying. So x cubed times -1 is negative x cubed, which is less than or equal to x cubed times the sine of 1 over x. Oh, that looks friendly, which is less than or equal to x cubed. No need to flip anything because we multiplied by a positive number. Well, now we've got in the middle x cubed times sine of 1 over x, which is where we started. So let's see if this squeezes. Maybe it won't, but hopefully it will. To squeeze, we hit everything with the limit as x approaches 0. So we get the limit as x approaches 0 of negative x cubed must be less than the limit as x approaches 0 of x cubed times the sine of 1 over x, which in turn must be less than or equal to the limit as x approaches 0 of positive x cubed. Let's plug and play. What's 0 cubed? What's the opposite of 0? Still 0. Ooh. So 0 is less than or equal to, we still don't do anything with the middle because we can't. We don't know how to evaluate this. This is why we're resorting to using the squeeze theorem. But we know it's greater than or equal to 0, so that's a start. And then on the right side, the limit of x cubed as x approaches 0. What is that? 0. What? So our limit, at least for our first case, has to be greater than or equal to 0 and less than or equal to 0. What does that lead us to believe? It's 0. If this were not an odd coefficient here, sorry, odd exponent, like if this had been x squared, we'd be done. Because you don't need to do cases with x squared because it's always positive. But since this is not that situation, we do need to do the second case. I'll do it over to the right. Case 2. This is when x is less than 0. When x is less than 0, x cubed also less than 0. So when we do this multiplication, we still get negative x cubed. We still get x cubed sine of 1 over x, and we still get x cubed. But now because we've multiplied by a number less than 0, the order of these inequality symbols changes. And then flopping this so that it's in the right direction, which we don't technically have to do, but it just makes me uncomfortable to see it written this way. We would have x cubed is less than or equal to x cubed times the sine of 1 over x, which is less than or equal to negative x cubed. Hit this with the limit. The limit as x approaches 0 of x cubed must be less than the limit as x approaches 0 of x cubed times the sine of 1 over x, which in turn must be less than the limit as x approaches 0 of the opposite of x cubed. We were just at this party. We know what these limits are. They're both 0. And so even if x is less than 0, we squeeze this limit in between 0. Bless you. Which allows us to conclude with confidence that the limit x as x approaches 0 of x cubed times the sine of 1 over x is in fact 0. Yeah, if it doesn't squeeze, then it doesn't squeeze. Then we need to pick a better starting inequality. Okay, one more. We're almost there. This one will go kind of quick, I think. I don't know. Depends how comfortable you are with absolute values. We'll see. I think it'll fit on the bottom of this page. We'll see. I got like that much room. Example 7. That can't be right. 7 examples in one day. Sometimes we can find the limit of a function even if we don't know what that function is. And the squeeze theorem allows us to do that. if you had some assurance that a function related to another known function in a given way, then you can sometimes determine specific limits about that function. So what am I talking about? I mean, if you somehow were able to ascertain that the absolute value of some function, we'll call g, minus 2, was always less than or equal to the quadratic function 3 times x minus 1 squared. This is what I was talking about, where we're going to basically squeeze this guy in between the two parabolas of 3 times x minus 1 squared and the opposite of 3 times x minus 1 squared. What am I talking about? Well, okay, so we're going to look for the limit of g of x as x approaches 1 without any idea of what g of x is. We'll be able to use the squeeze theorem here to figure it out. Now, a distressing amount of students in Algebra 1, sorry, not Algebra 1, in first period, so this is an Algebra 1 topic, were fascinated by the revelation, dyslexia, that the absolute value of a number being less than some other number gives you a compound inequality. Okay, and so I actually ended up having to do this, which is fine. I don't think you need to write this down because you all took Algebra 1. But remember that if we say the absolute value of x is less than 2, that is not the same as x is less than 2. That's certainly part of it. X does need to be less than 2. But somebody tell me, is negative 18 less than 2? Yeah.
What's the absolute value of negative 18? So the absolute value of negative 18 less than 2? No. So to just say, yeah, everything left of 2 is not enough. Because eventually, yeah, left of 2, 1, that's cool. 0, that's cool. Negative 1, that's 2, cool. Negative 1.9, that's cool. As soon as we get left of negative 2, the absolute value of those numbers are not less than 2. So that's where the compound inequality comes from.
Is that if we have the absolute value of some number less than some other number, it means two things. Yes, you are less than that number, but you are also greater than the opposite of that number. You're also greater than the opposite of that number. And so what I'm about to do here is just to apply that. I know it looks scarier because there's g's and squares and whatever, but we're about to just do this. That if this thing, g of x minus 2, has an absolute value less than this thing, what that means is that this thing, g of x minus 2, yes, for sure, is less than 3 times x minus 1 squared. But it's also greater than the opposite of this, which is negative 3 times x minus 1 squared. This is just Algebra 1 with slightly scarier stuff. Absolute value less than means this. Well, they're asking us for the limit of g of x, and I currently have g of x minus 2. Let's just rearrange. We add 2 to both sides. We'll have g of x is less than or equal to 3 times x minus 1 squared plus 2, which must be greater than the opposite of 3 times x minus 1 squared plus 2. Now let's see if we can squeeze. We got the thing in the middle that we want. The specific limit we're looking at is for x approaching 1. This would turn into the limit of the opposite of 3 times x minus 1 squared plus 2 as x approaches 1 is less than the limit g of x as x approaches 1, which in turn is less than or equal to the limit of 3 times x minus 1 squared plus 2 as x approaches 1. Whew. And our deepest desire is that the left and right share a value, because then we will have squeezed g of x in between. Let's plug and play. Plug in a 1 here. What's 1 minus 1? 0. What's 0 squared? What's 0 times negative 3? What's 0 plus 2? Oh, thought somebody was going to say 0. 2 is less than or equal to the limit of g of x as x approaches 1 on the right side. Plug in a 1. What's 1 minus 1? What's 0 squared? What's 0 times positive 3? What's 0 plus 2? Oh, 2. Would you check that out? I don't know anything about the limit. I don't know anything about g of x. I don't know its rule. I don't know its friends. I don't know its family. But somehow we've just shown that as it approaches 1, it has a limit of 2. It really wants to be 2 as x approaches 1. Thank you, squeeze theorem. You're the best. Whew. And that finally, Mr. Herrick, is LP. The end. Select for me. We're going to amend your homework. And this is the rare case where I'm going to review more. So cross out what's there. It just says 1.1, should say 1.10. We're going to keep this simple. You're going to do numbers 1 through 19 odd. So those 10 problems are all using the new Trig tricks. And then make sure I have right numbers. Stop. Deep row. Stop. And then, so those 1 through 19 are the trig identity stuff. And I also want you to do 29, 30, and 31. And those 3 are squeezed out. So it's really not that much. Just give you a chance to practice. So Thursday this will be due. And then on Thursday we will tackle the delta epsilon group. Oh, and I just stopped recording notes. Get that on the YouTubes.